Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment&Health. Eco-Environment&Health is a journal initiated by prestigious scientists with a strong editorial board including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design and broadcasting. The experts will accompany you like a harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision making that deeply integrates informatics, ecology and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Hi, Patana, are you here?
Yes. Hi.
Yes, thank you. Glad to meet you. Okay. Long time to not see you. How are you?
Good, good. How are you going?
Yeah. How about Albert?
Yeah, he's good. I'm actually in America at the moment, so I don't know how he's doing right now.
Okay,
Yeah.
okay. So it's time. Maybe we can start the presentation. Okay. Hi everyone. It's time. It's 9 o'clock in Beijing time here. So we are very glad to invite Dr. Fatjana Kasturi to be here, give us an oral presentation on bioavailability and bioaccessibility of arsenic in mining impact soils. So before the presentation, I will introduce Dr. Fatjana. She is a well-known scientist on bioavailability and bioaccessibility of metals, especially metals. I know she is just also doing some work on organic protein recently. So she is a very well-known scientist on bioavailability of metals in soils, and also she works on inhalation bioaccessibility or bioavailability of metals. She received her PhD degree in 2019. After that, she worked from the University of South Australia. Since then, she worked there and as a research associate. Also, from since April of this year, she go to America and works as a a Fulbright scholar, yeah, in the Columbia University. That is now. She okay. Just also she published many papers on the bioavailability and the bioaccessibility of metals, especially lead and arsenic. So she had a lot of story here. So today we invited Dr. Fernanda Castillo to give us an oral presentation on bioaccessibility, bioavailability, and the speciation of arsenic in the gold mining area. So let's welcome Dr. Castillo to give a wonderful presentation. Okay, let's start. Okay, thank you.
Thank you so much, Hongbo. That was wonderful. Thank you for that introduction. Let me just go back to the first page. Can you all see my first page now? Just
yeah, we can see. Yeah.
Okay, awesome. All right, so I've got about an hour, so hopefully I'm not going to take that long, and I'll have some time for questions. Before I go starting my presentation, I just want to say thank you to all my collaborators of this project, especially Julie Orr, who was a really good summer student and did most of the work. Aaron and Kark helped me with the speciation. Richmond did some of the XRD work, and Pasi Netherway is the contact from the Environmental Protection Agency, who is going to hopefully find the results useful for their policy making. And lastly, Albert Juhas, which several of you may know, who is basically my PhD advisor and helped me conduct this project as well. So I hope you understand me, because I know I have a bit of an accent. And if you don't, just please just unmute yourself and ask questions at any time. I really don't mind being interrupted at all. So for the presentation of this story, there is going to be a hero and a villain. Let me introduce you the hero, which is gold, and the villain is, of course, then arsenic. So when we think about gold, we generally think it's a noble material. It doesn't react with anything, and it's basically something very well sought. Like everybody's spends a lot of time over the last 100 years looking for gold all around the world because its beauty and allureness. On the other hand, arsenic is a very well-known poison. But the fact is that arsenic and gold have been fated together, and they're always found at the same place. So wherever there have been gold mining in the world, there has been a major arsenic contamination as well. And it is probably true not just for gold, but for a lot of other metals, because arsenic co-occurs in the same ore for a lot of these materials that we want. I'm not a geologist, so I'm not completely going to be able to explain this graph at the bottom. But what generally happens is deep in the belly of the earth, where there is high heat and magma and everything is swirling around, they find their way up towards the crust of the earth because of little faults that pushes all of the magma like this upwards in the trajectory of the earth's crust. And as it comes up, a lot of the time, if there's a lot of gold in that magma, the gold becomes attracted to pyrite, which is an iron sulfur material. And if there's arsenic in that, if there's arsenic occurs together, then arsenic drives the concentration of gold in the deposit. So arsenic makes it easier for the gold to get into the pyrite or other minerals and concentrate in there. And then a little pockets like this is where gold deposit occurs, and millions of years later down the track, we dig it up and we try and separate the arsenic from the gold and all of the other precious materials. Now, I'm going to introduce what the Victorian goldfields are and where in Australia this is. So this is a map of Australia. And to all the participants here, if you haven't had a chance to visit Australia, I'd like to warmly invite you now. You must come over one day and look at this fascinating country. So I am from South Australia. I work about here generally. The area I'm talking about is this one in red. And this area, Victorian Goldfields, is known well around the world for the amount of gold deposit it had. And in this big insert here, I've just put these labels here, just tell us about where the goldfields were. The most famous of them were Bendigo. And this place alone had more than 8 million ounces of gold was produced. And as you can see, quite a few of them are over 5 million ounces. And then this whole gold field has basically been the source of Australian gold for nearly 60 years. The first gold was discovered here in 1823, so that's nearly 200 years ago, and people didn't quite catch on to it quite quickly. Gold was rediscovered 1850 by some prospectors, and that was about the same time as the Californian gold rush. So everybody was super excited, and they all rushed to Victoria to start getting the gold. A lot of the gold was initially found as alluvial gold, which basically means when there's a nearby ore and it weathers, like it erodes a little bit and the gold gets loose and it flows with the stream nearby river. And it just, you can, back in 1850, you could have found the gold basically lying in riverbeds, and all you had to do is, like these two gentlemen here, just get this little device and where you can just pan for gold, and of all the gold discovered, nearly 40% of that was found just like that. Just before the First World War I, the gold started to dwindle, and by about 1954, we've dug up all of the available gold, and no one was really interested in the commercially available gold anymore. So in this time, there was about over 2,500 tons of gold discovered from this region alone, which is a little bit hard to fathom how much that is. So that would be about 2% of the whole world's gold production that came from that little place in Victoria. So once all the alluvial gold is finished, the ones that's just lying in the riverbed, what's left is gold that's buried deep in the earth. They're often found as fine particles in these minerals, like you can probably see little specks of gold there. But most of it would be bonded with pyrite. Pyrite is an iron and sulfur mineral, like this here. This is used to be called fool's gold. I think it looks like gold, but it's not very easy to get the gold out of there. So what the different processes that were utilized at this time to get the gold out has a direct consequence of how the arsenic was concentrated in the refuse, like in the waste material of this gold processing. The first thing that you had to do is physically separate the gold from all the, the gold bearing material from the rest of it. And the first of all, you had to dig up the area that you think there will be gold, and then you have to crush it. So this was basically quartz, so very big rocks. And you can see this is one of the devices that used to be used, and they have like 1, 2, 3, 4, 5, 6 stamps. And you'd put the soil in here and turn this wheel here, and it would just go up and down, up and down, up and down, and crush all of the material into quite a small pieces. And then you put all of those smaller pieces with water in a slurry in a tank, and you just swirl it around for a long time. And as you may know already, gold is very heavy. So it's much heavier than sand and silt and rocks. So it goes to the bottom. So you get rid of all the bit from the top, and what you get is a concentrate. From that concentrate, you apply further chemical separation, like you can dissolve the gold and some other metals like silver with mercury, or you can put cyanide through that slurry, and cyanide tends to dissolve gold. And that's how you can separate the gold-bearing fraction from the non-separated fraction. So as you can see, just from this very little introduction, there's a lot of mercury contamination of this area, just as much there is cyanide contamination as well. So the one last processing that's very important to our topic today is that they came up with this system where they used to have all the slurry, that's the end result of all the crushing and milling. And they used to put this slurry in a massive, massive furnace, and they used to roast it over 500 degrees Celsius. And what that typically does is it burns the sulfur from the pyrite. So if gold is bonded within iron sulfur minerals, so you you burn off the sulfur and it becomes sulfur dioxide and goes into the air. And what you're left with is iron oxide rich residue. So this process actually converts the iron in pyrite into hematite, which is, you can see on this right-hand side here, it's deep purple colored waste material. But what happens is when there's arsenic in this pyrite, or it is arsenopyrite, this process actually burns the arsenic as well. And then the arsenic becomes arsenic trioxide, which is a highly bioavailable form of arsenic. So it goes in the air and then it precipitates back into the very area that you're doing the roasting in. And although a lot of the arsenic is burned off as arsenic trioxide, these waste material often contain very high arsenic residue as well. So at the end of all of these 60 years of digging, what happened is, with all the slurry that they've extracted the gold material out of, whatever's left, because it was 150 years ago, there wasn't a lot of environmental regulation back then. So the easiest way to get rid of them is just put them in the river. So basically everything downstream from where all of the processing activities happened gets swamped with this sludge. You can see here, this riverbed has been just, basically there's no more water in that river, it's just sludge from all of the all of the gold processing minerals. So this is what we're talking about. This is what's left after 150 years of gold mining in this area. So a lot of work in gold and arsenic has been done in Canada, in New Zealand, in America, and parts of Europe, but there's very little research has been done specifically for the Victorian goldfield gold mine wastes. So the aims of this study are, first, to collect and process as many as 30 samples, because we wanted to have high statistical power. So we collected 30 samples, we dried them at 40 degrees Celsius and sieved to less than 2 millimeters just to get the samples ready. We fractionated the soils into 3 particle sizes, so not only the particle size that's relevant for ingestion, but smaller ones that can be windborne and get into people's houses, for example. We did a lot of physical characterization, and then we did exposure assessment, and they were the in vitro and in vivo bioavailability that I'll talk a little bit more about. So let me explain some of the methods that I've employed. So on the bottom here, I've got here is the calcine sand that I already showed you. It's the result of roasting of all the ores, and it's very characterized by dark purple color. And I've got 7 of them in my study, and I've called them C1 to C7. Second type of mining waste I've got here is gray sands, which is when you're putting all of the crushed particles in with water and made a slurry, and you rotated that for quite a long time to separate the gold. All the fine particles typically settle in the bottom of the tank, and they're just called, gray sands in my paper. This is fine gray particles. I've got about 11 of them, and they've been termed G1 to G11. And finally, all of the tailings are basically whatever that couldn't be classified as either this or that. So this one here on the right-hand side just represents the background material texture of the tailings, basically what we call them, which contains particles of any size, any color, any texture. And I've got about 12 of them in my sample, and they've been named T1 to T12. So for the size fractionation, after we've got the 2 millimeter, we have the less than 250 micrometer, which is incidentally ingestible, which is basically means in here you can see there's particles that stick to your hand when you play with sand. And this is very possible that if you haven't done a good hygiene and you haven't washed your hands straight away, this is possible that throughout the course of the day, because of hand-to-mouth activity, you incidentally ingest some of this material. The less than 53 and less than 20 micron particles I have also collected, because it's a very well-known phenomena that smaller particle sizes tend to be more enriched in arsenic and typically all inorganic material. So for these two, I'm a proxy for house dust. Now I've put a question mark here because although there's pretty good nationally agreed micron size for incidentally ingestible stuff, there's really no guidelines for what is considered house dust. So I've got these two fractions as those that represent particles that's easily easily wind blown and easily get into the house and possibly act as house dust and get incidentally ingested from there. The physicochemical characterization was quite standard. So I've used 0.05 to 0.5 gram of sample to do aquaregiodigestion, and metalloids were analyzed via ICP-OES, and they're all followed standard USCPA methods. I've done pH measurement in water, so soil to water 1:5 ratio. I've done XRD in the less than 2 millimeter and X-ray absorption spectroscopy to get the speciation of iron, lead, and antimony in the less than 250 micron only because it's quite time consuming, and I already asked for so much from CARC, so I didn't want to bother them with the lower particle sizes as well. For the exposure assessment, I've employed in vitro bioaccessibility, which is the USCPA method 1340, and it's only the gastric phase of the SBRC. I think a lot of you may know about that. And I've used all 3 particle size fractions to put through this bioaccessibility method. And I'm going to show you results of arsenic, cadmium, lead, and antimony as elements of co-contaminants of interest in this paper. So the calculation of in vitro bioaccessibility was also standard. Whatever is soluble, whatever soluble over total times 100. Selected samples were also fed to mouse in a 10-day study at 3% of the sample was mixed in with their diet. And I've used urinary excretion factor as the biomarker for this project because there's a very good correlation between arsenic and urine that's been established for quite a different animal model. And for the RBA, I've got a ratio of absorption of arsenic from the soil to absorption of arsenic from sodium arsenate, which is the toxicity reference value, times 100. Now, I will move on to some of the results now. The first result I'm going to show you was the XRD outcomes. And I'm going to point out the way I'm going to present the results to you. So I'm going to always have it in this format, so it's a bit easy to compare, which the first sort of results will be the calcine sands, which is C1 to C7, and then there will be the gray sands, which is G1 to G11, and the last one will be the tailings, which is T1 to T12. So if you just quick look at this graph, you can easily see that the most of the sample, and up to like 70%, is basically quartz. This is basically because the type of ore that was found in that specific area was really high in quartz. And the second thing you may notice is all of the calcine sample have very high hematite concentration. And that was also expected because, as I mentioned, the process of roasting converts most of the iron oxides into hematite itself. And this is just the proof that, yes, there were a lot of hematite in these samples. And lastly, there were a lot of mica that was found in the gray sands, which is very, very small particle size as well. And tailings are just a heterogeneous bunch of everything that's left over. I'm going to show you the total arsenic first in the less than 2 millimeter particles. And again, I want to point out the way I'm going to show you the results. The calcine sands will be in purple, just to make it visually distinctive. I've put all the gray sands in gray and the tailings as black. And I've also put something called arsenic health-based investigation level A, which is the trigger value of arsenic investigation in Australia. This is for residential area with a bit of open space where children can access soil, and about 10% of the produce that's grown in that soil as well. And the trigger value of arsenic in Australia is 100 milligram per kilogram. And I've indicated that with that red line here at the bottom. Now you can see very quickly that all but one, just 29 out of the 30 samples I had exceeded that HILA level of 100 milligram per kilogram. So this is partly intentional because I did choose the ones that needed further investigation. So I did choose from the bunch that had high arsenic as well. But let me just show you how high this arsenic is. So the calcine soils have between 40 to 160 times the HILA value. Like 6 out of the 7 is really exceeding this limit. There are quite a few in the gray sands that's exceeding limits quite well, like a few magnitudes higher, and the tailings are really quite variable. Some of them are quite low, some of them are quite high as well. But the main culprit, as far as I can see from this graph alone, is the amount of arsenic that's in calcine sand is quite astonishing. So let me show you some of the co-contaminants now, because it's not just arsenic that's found in here. So cadmium is also very high in calcine soil, and the trigger value for cadmium in Australia is 20 milligram per kilogram. So you can see at least 2 of these calcine sands clearly exceed the limit, and the rest of them are very close to the limit. In contrast, there is hardly any cadmium detected in the rest of the samples. Only one was detected marginally in gray sands, and one was in tailings that I could see. Again, antimony is very similar to arsenic, that it tends to concentrate with gold and helps, it follows the same geothermal mechanics. So it's often found to co-occur in the ores that gold is found in. Now I've put it here as assumed antimony health-based investigation level, because antimony is an emerging contaminant. We don't actually have a trigger level set for arsenic nationally. Antimony nationally, but there is quite a good argument that arsenic and antimony have very similar structure, similar oxidation states, similar sort of behavior in the soil and water interface. Therefore, it may possibly have the same sort of toxicity trigger value. This is just a proxy, I can't be sure, but at this moment, I'm just saying that assumed antimony trigger value is 100 milligram per kilogram, just same as arsenic. And you can see that 4 out of the 7 calcine soils have quite high antimony, and one of them at least have like close to 6,000 milligram per kilogram of antimony. And we just really have no information in the literature about the behavior of something like antimony in these samples, because it's not a common contaminant, co-contaminant that you study in this sort of area. And lastly, lead. Lead is pretty much the same. All the calcine soils exceeded the lead trigger value of 300 milligram per kilogram. And one in particular was nearly 9,000 milligram per kilogram. So that one was really quite high. So as you can see, just very quickly from these 4 graphs, when looking at arsenic contamination in the gold field, which people generally do, people generally go and look at the arsenic, but it's very, very important to look at all the co-contaminants as well, because having a waste material that have multiple co-contaminants just means that the toxic load on people and the environment is that much higher. So next, what I'm going to show you, I've just shown you all the arsenic in the less than 2 millimeter. So this is a graph of how this is enriched in the lower particle size fractions. So this graph here, it represents the ratio of 250 micron to 2, and you can see pretty much all of them are close to 1 to 2. So the enrichment is not great between these 2 particle size fractions. So if you look at something, this next smaller one, this is a ratio of 53 microns divided by 250 microns. And you can start seeing that trends of calcine sands not having much enrichment, but some of the gray sands start to go beyond 2. And this trend is even more visible if you look at the smallest particle size, which is, I've got here is 20 micron over 53 micron. And again, you can see that the calcine sands don't get amplified as much as the gray sands. So by definition, the gray sands have very small gray particles, and which is probably why there's a lot more of the smaller particles in this type of mine waste, which also means that potentially these sort of mine waste can be aerosolized a lot quicker and come into people's home and present more toxicity results. Okay, that's what I want to say, that exposure from the finer particle will vary depending on the waste type as well. Now, I'll show you the results of the bioaccessibility now. So I'll just show you results from the 250 micron first. And as you can see, the overall median bioaccessibility for all of my 30 samples was about 42.7%. And a lot of them, there's quite a few that's higher than median in the calcine soils, calcine sands. There are a handful of them higher in the gray sands, and only 3 of them are higher than the median in the tailings. So most of the lower value of the arsenic bioaccessibility is coming from the tailings, which that's probably the least problematic of all the types of waste that is available in a Victorian waste field. But if you think for a minute that even the 80% bioaccessibility of a very high total metal content is a lot of arsenic. So all of them are representative, really, all of them pretty much is representing high risk to human and the environment because they're quite bioaccessible as far as I can see. Now, I want to relate their bioaccessibility to speciation of arsenic found in these samples. So this is the same graph as before. I've just put that here for reference. And on the right-hand side, I've got all the arsenic speciation here. So the first thing you'll notice immediately is that these first 6 samples are quite different from the rest of them. The first 6 samples are these, which is, you can easily see as well, it has quite high bioaccessibility. And the reason being, these are split between euconite, which is a calcium arsenate, and arsenic co-precipitate with calcite. And both of these forms of iron species are known to be quite bioaccessible, like they are the most bioaccessible range of all of the arsenics. And the rest of them, we've got a little bit of the rest of them. The most dominant phase is arsenic sorbed onto iron and aluminium. And what happens is the sorption over time is stronger than desorption. But it depends, but the bioaccessibility will depend on the amount of iron, amount of aluminium, the type of reactive iron. So although this looks like most of it is arsenic 5 adsorbed onto aluminium iron or as ferric arsenate, there's large variability among these species itself. So it's not that those two, because they're similar percentage of aluminium adsorbed onto arsenic adsorbed onto aluminium, will yield the same bioaccessibility, because it depends on a few more factors, like how strongly it's adsorbed, how much aluminium, how many iron there are. And as you can see here as well, G2 and G3 are quite similar, but G3 and G4 is different. So this large amount of variability in this is presumably a result of this, the variability in the speciation. But a couple of things I want to mention is that this one, G11, T8, T9, and T10, these actually contain arsenopyrite, which is the form of arsenic-bearing minerals that's in the ore itself. So it seems like they have either not been changed into anything else as a result of all of the chemical and physical treatment, or they have become reduced over time as well. And you can see that this specific one is known to be quite the least bioaccessible of them all. And you can see here G11, this explains why this one is particularly low in bioaccessibility among all of the gray sands, because it has high arsenopyrite. And T8, T9, and T10 is here, T8, T9, and T10. All of these also have fairly low bioaccessibility, and it can be explained with these 3 speciations at least. So I want to quickly also, like this is again the same graph as before, just for reference. So I want to also explain the result of this bioaccessibility to the total concentration. So on this x-axis, I've got total arsenic concentration in the less than 250 micrometer. And on this hand, arsenic bioaccessibility, but this time it's not in percentage, it's in milligram per kilogram. And a couple of things to notice. First thing is that This is the dotted line is the 95% confidence interval, and the dashed and the solid line is the regression line. And you can see there's very good relationship. The R-square is 0.85. They're very tight, except for like one rogue one here and just a bunch of them here. Everything else pretty much falls in line. And it's most of the bioaccessibility, except for these ones, can be explained or is related to the total metal concentration in these particles. And the second thing you'll notice here, which I will allude to towards the end of the study as well, at the end of the presentation as well, that the slope of this is 0.46, which is about 1-to-1 relationship. And same here, the bioaccessibility of less than 53 micron, it is almost identical. The bioaccessibility is 42%. It doesn't change overall median, and this equation doesn't change all that much. There's a few more of these deviations, but the slope is about the same. Then it's a very strong relationship as well. And surprisingly, it's exactly the same for the less than 20 micrometer. Overall median bioaccessibility is very similar. The slope is very similar, and the R-square is very similar, although there is a lot more variability. I can see a departure from the 95% confidence interval. But you can see that for all of these soils, all of the different soil particle fractions, it's mainly bioaccessibility is mainly related to the total arsenic concentration. So this is an interesting one. Out of all of those bioaccessibility results, we've got a selected few we fed through the mice. And again, the red ones here is calcined sand, the gray ones is gray sands, and the black ones are black sands. For comparison, I've got these solid lines, which is the total arsenic. This is the bioavailable arsenic, and on top of it, I've just put the percentage here. So again, like last time, what we could have predicted, because of the total amount of arsenic available, the bioavailable arsenic is also high in these calcined sands the most. The notable one among these is this one, which is quite low, 13.6%. And I know I don't have the graphs before me, but all these four had very similar bioaccessibility, hovered about 45%, had very similar arsenic speciation. They were split between calcium arsenate and arsenic co-precipitated with calcite. But this one here is significantly lower than the other three. And I had to actually look at all of my tables and all of the results and figure out why that has lowest arsenic bioaccessibility among the calcined sands. And the reason that I've come up with, the way to explain it, this specific sample had more calcium than the rest of them. And although calcium arsenate, sorry, I'm just tipping over all of these, tends to have very high bioaccessibility, as the from when the sample's going from the stomach with low pH to small intestine, which is high pH, the change in pH tends to precipitate arsenic with the calcium if there's an excess calcium in the system. And some of this arsenic may be precipitated as heterogeneous particles, which is then taken out of the solution. And that's most likely why this one had significantly lower arsenic bioavailability than the rest of them, which goes to show that also, although bioaccessibility is a very good measurement, generally speaking, we still have to do, every now and then, we do have to do the bioavailability assessment just to look at all the complex interactions between our contaminant of interest and cations during absorption, which is not quite reflected in an in vitro study. And among the gray sands, they were quite high arsenic bioavailability as well. Only this one here, the T11, the bioavailability was less than 100 milligram per kilogram, which is the trigger value. So all of the 7 out of the 8 that we fed to the mice had arsenic bioavailability at a rate that should be quite alarming, and they should be investigated further. Now, I'm sure I mentioned before that I'll come back to this graph again. So this here in the solid square ones here was my bioaccessibility result. So bioaccessibility on this side and by total metal on this side, and the slope was nearly 1 to 1.47. And I've done the plot again with bioavailability, which is represented by the circles here. And straight away, you can see that the slope is a lot lower, 0.28, although it's a very good strength of the relationship is very good. So what it really means is at the higher end of the arsenic, as the total arsenic goes up, the absorption is not as high as would have been predicted by the bioaccessibility results, which is probably because at this point, the arsenic is so high that it's probably reached the limit of absorption, because there's only a finite amount of time these samples would be in the gastrointestinal system, and also because these have very high iron, very high calcium. So all of these different cations is also competing for absorption. So on first look, although it looks like a lot of the calcium, a lot of the arsenic, as concentration goes up, the bioaccessibility goes up. But when you do the bioavailability measurement, it's sort of, the slope is a little bit less steep, which is good news. If it were the other way around, that the IVBA was under predicting RBA, then that would have been a problem. But for now, this is actually a good news, because this, if we do bioaccessibility alone, it gives us a very good conservative measurement of what's going on or the potential risks. So for the last few minutes, I'll just quickly show you a couple more slides, but I'll go through this a little bit quicker. So if for those of you who are interested in having an equation that uses arsenic IVBA to predict RBA, I have good news that US EPA 1340 can be used quite reliably. So you can see the strength of the relationship is 0.86, and it's got a pretty good slope, and most of the values are within the 95% confidence interval. Just this one had high calcium and had lower bioavailability, as I mentioned before. Last three slides will be about other co-contaminants. The first one I'm going to be talking about is cadmium. So although we saw that these two had nearly as much as 20 milligram per kilogram of cadmium, which would have posed a risk, the cadmium bioaccessibilities are quite low. Most definitely, they're lower than 8 milligram per kilogram. And I haven't done any in vivo measurement of these, but if that's an overestimation, as same as arsenic, then it's probably safe to say that the calcium doesn't pose as great a risk, cadmium doesn't pose as great a risk as arsenic does from this mining impact sample. Last one is antimony. And again, I must emphasize that we don't know the trigger value of antimony, but it can be assumed to be 100, same as arsenic. And as you can see, the bioaccessible antimony in these systems are less than 60 milligram per kilogram. And this sample in particular had of nearly 6,000 milligram per kilogram of antimony, and only 60 was bioavailable. So this is very in line with the literature that antimony solubility is very, very low. So without more investigation, I can't quite say, but this, I would assume that this is quite low. This presents, although this total antimony is ridiculous in the samples, it presents quite a low risk from these samples. And last thing I want to point out is lead. Now, all of these gray sands and tailings had less than 90 milligram per kilogram of bioaccessible lead, whereas all of the calcined sands had, I forget what this is, but that's probably 900 milligram per kilogram and above. So that is well above 300 milligram per kilogram, which is produces a risk in total soil. So one thing, if you want to watch out in these, the one co-contaminant you want to watch out for in these soils is going to be lead. So just to quickly wrap up the discussion, I think I am maintaining time, so which is good. So calcined sands, which is the sands derived from roasting, high temperature roasting, has the highest concentration of arsenic and co-contaminants of interest. So if you are short on money and you want to focus on something, you should focus on calcined sands as the first point of remediation or removal from children. So among the co-contaminants of concern, lead appeared to pose the most risk, while antimony and cadmium bioaccessibilities were low, but we do need to do more investigation to understand the risk behavior or mobility of these elements in soil. So although arsenic bioaccessibility using USEPA method 1340 and speciation combined with speciation is very good predictor of bioavailability, at some point we do need to verify this with some RBA assays, because certain factors like cation concentration, as was the case for this one, was calcium, may influence arsenic RBA as well. So we found in this study that it was reducing bioavailability, but we should look at this more thoroughly to see if there's a synergistic behavior as well. And the good news that when ended, arsenic RBA is most likely going to be lower than what's predicted by the bioaccessibility results. And we do need further investigation for this. We're using Victorian goldfield soil, but that probably means that within budget, animal ethics, and cost time concerns, arsenic bioaccessibility can be used quite reliably to predict the exposure from Victorian soil. So I just want to end my presentation saying thank you very much for all those that turned up. It's very good audience, 37 people. And in times of COVID, it's been so hard to reach out. And I really want to thank you, all of you, for coming and listening to my talk. And I can see a couple of questions in Q&A, but I'm happy to stick around, or I'm happy for you to email me using this email if you want, if you're interested in anything you want me to explain further, or if you have potential projects that may, you would like to ask for collaboration from me. I'm really open with all of these. So shall I go ahead and look at the Q&A just to see what questions they have? Okay, so first one is from Shui Li.
Okay.
Hey.
Okay, thank you, Brenda. It's a very good story here. Okay, did anyone have a question here? You can ask. Okay, I have several questions from here. I'm very intriguing to get the story here. One soil from the calcium soil C6. Yeah, in the mouse, the relative bioavailability of the C6 soil is very arsenic bioavailability is very low. Yeah, this you think that it is due to very high calcium concentration. Yeah, I strongly agree with you. Yes, we just found that if a diet very high in calcium concentration is fed to the mouse, the high calcium concentration can lower arsenic absorption by the mouse. We just we just did an experiment to show that when we fed mouse with calcium, then the arsenic bioavailability in mouse is lower, very much lower. Yeah, but we found it is maybe another reason can explain this, because we found that when the mouse is fed a very high concentration of calcium, the intestinal phosphate transporter, yeah, can be lower. Yeah, because lower, then the arsenic absorption from the phosphate transporter is become lower. So maybe this is another reason for this. So this is very interesting. We just found this. Just discuss with you. Okay.
Yeah, of course. Yeah.
Maybe also I think this is we can do some more work on the influence of calcium and arsenic bioavailability here. So this is a very interesting story. Okay, another question is why you only analyze only 8 soils for the mouse?
Oh yes, as you know, we try to do all of the bioaccessibility study so we don't have to put it through the mouse, because we want to reduce the use of animals as much as possible.
Okay.
So we wanted to have the least possible mouse animals sacrificed, while we wanted to have a variety of the sample. So we picked things from, you know how, let me go back. So from this example, I picked like some from very high, some from low, some from middle.
Yeah.
And I wanted to represent some from calcinated, some from gray, some from tailings, but I didn't want to kill all that many mice. So that's basically why I chose 8. It's a random number, but at 8, I thought I had a good representation and I'll be able to corroborate my story without sacrificing more animals.
Okay. Also, I have another comment for you. We think that because the soil are contaminated with arsenic, lead, and also
antimony and cadmium.
Yeah. But however, when you fed the soil to mouse, you used urine for arsenic bioavailability assessment. But in my idea, I think that we can also use lead or cadmium concentration in tissues
Yes.
like liver and kidney for
Yes.
bioavailability analysis. So maybe you can use the same mass, because I'm wondering, did you collect liver and tissues for this mouse?
Yes, so we collected liver, kidney, and bone for this mouse, and the bone we chose was femur. So that's using our established techniques. I haven't put those figures in this paper because that will be another paper.
Yeah.
So I didn't want to put all of them in this one. That because arsenic is my main contaminant here.
Yeah.
So I've tried to use all of the bioaccessibility, everything else to support that there is other contamination. But Albert and I will write another paper where we'll have all of those data available. But if you're curious, I'll just send me an email and I'll tell you the results.
Okay, wonderful. Yeah, thank you. I just have these questions for you. Okay, did anyone have another question for Dr. Kasturi? Okay.
I can see a few questions in the Q&A section and some things in the chat.
Yeah. Shui asked 2 questions, 3 questions here. Do you know Shui?
It's I know her from papers.
He got his PhD in Nanjing University. He's a PhD doctor of Dr. Ma. Yeah.
You can ask your question directly, Shui, if you like.
Yeah, Shui, can you ask directly? Maybe she is not online on the web.
Yeah. I'm trying to just read the questions quickly because it's quite a big question. Okay, very interesting to see your topic presentation. So the very important impact of particle size for this study, which I can probably go back to here somewhere.
Yeah.
Oh, maybe I'll show it with this one. Am I still sharing screen? I am, aren't I? Yep, I think. So you can still see the screen. That says arsenic enrichment. Can you, what can you see? I'll just stop sharing and I'll start sharing again. So can you see the screen that's got arsenic enrichment now?
Yeah, we can see.
Okay,
yeah.
cool.
Okay.
So the very important factor I found for this is that if you look at the x-axis and just look at this one, that's the highest calcine. It's about 1,500, just a little less than 15,000, sorry, not 100. And as the particle size goes smaller, it's reaching about 20,000 now, 17,000, just guessing. So that's the very important factor, that as the particle sizes get smaller, there's more and more arsenic in those, same mass of sample. So that's although the bioaccessibility doesn't change, so it's still 45%, around 45% bioaccessible, but because the total amount of arsenic is so much higher in the small particle sizes that the total exposure is higher. But I haven't seen any effect on bioaccessibility from my samples on arsenic particle size. So that was the first question, I think. Second one is, I'd like to know those findings, whether will have an impact on the particles. I think it's the same question.
Yeah.
Oh, sorry. So same question 3 times? Yeah, I think so. So
Yeah,
I think
yeah.
I just answered that. So what I wanted to see is basically whether or not there's an impact, like Shiwi asked, if smaller particle sizes have higher bioaccessibility. But it seems if you just look at the percentage, it's the same bioaccessibility, but the total is higher, therefore its total bioaccessibility is higher.
Okay.
If that makes sense.
Yeah. Okay. Okay. I'm just thinking about another factor. Because the C sample is from the roosting residue. Yeah. The soil labeled C. Yeah. It is from the roosting residue. Yeah. Roosting.
Roasting. Yes. Yes.
Yeah. Yeah. Okay. So for this soil, I think they sort of contain very high concentration of iron. Yeah. So maybe I from the PowerPoint I found that the bioavailability is lower. It's always much lower than the in vitro bioaccessibility. Yeah. Much
Yes.
lower. Yeah. So
Yeah.
so did iron cause the finding? Because when mouse or fed soils with very high concentration of iron, the iron may be reduced, may reduce arsenic absorption. Yeah. So
yeah, that's a very good point. I was wondering what's causing this. And to be fairly honest, I can see that same thing with gray sands. I don't know if you can see my screen here that says relationship between arsenic RBA.
Yeah.
So as you can see here in the gray sands, which didn't have a lot of arsenic, I mean, a lot of iron, there was a difference here. And the differences were, one of them were higher bioaccessibility than bioavailability. The other one was higher bioavailability than bioaccessibility.
Okay.
And
okay.
the difference was also in tailings. So it's not that, now it is possible that the iron itself is causing the differences in the higher ends. So what I would need to do in this case to fully explain that is have similar arsenic of different types of dust, different types of soil. Like, for example, I need to have a similar arsenic concentration in gray sands and feed it to mouse and see whether or not how, having the iron, how that's interacting. Because all of these are very highly crystalline iron as well. So it's possible the iron doesn't dissolve quite as much.
Yeah.
From the, there is iron there, but probably it doesn't dissolve quite as much. And I'm saying that because Cam Olson et al., who published a similar work before, he did more work on reactive iron, and he found that there was reactive iron concentrations were low in calcined sands. So although there's high iron, but they may not dissolve quite as much. They may not have reactive iron quite as much. So we just need to explore this a lot further. At this point, I'm unable to answer your questions because I don't have enough data. But from what very little data I have, I would tend to say that this iron is not that easily soluble, so it may not have that much of an impact.
Okay.
But if it were any other type of iron, probably, sure.
Okay. So it is the role of the calcium, not iron.
For now, the only difference that I could see is calcium that's making an impact. But like I said, if I have different, same arsenic concentration, but different type of sample with different iron, then I could probably tease it out that what effect that iron is having.
So I'm just intriguing. What is the concentration of the calcium and iron in these soils?
So this last one, the one that I showed you, was a problem with the significantly lower arsenic. Yeah. This one had, as far as I can remember, about 7,000 milligram per kilogram calcium, whereas the other three had about 5,000. So it's not that much. Yeah, it's high, but it's not like twice as much. It's still 2000 milligram per kilogram high, but not, that much. So even a little calcium would make a difference by the looks of it.
Yeah.
Yeah.
I guess, yeah. Okay. Interesting. We learn a lot about the story about arsenic by accessibility in short impacted by gold mining. Yeah. So any questions here? Okay, there is no more questions here. So thank you very much, Dr.
That's okay. Thank you everyone for coming. I really appreciate the invite. If if you'd like to continue this conversation, just email me or.
Okay. Okay.
Thank you. Have a
Thank
good
you.
day.
Have a good day. Then maybe we can when it is okay, we can meet. We can also invite you to be here in China or in Nanjing
Sure.
here. Okay. Okay.
That sounds good.
See you next time.
Okay.
Okay.
Thank
Bye
you.
bye.
Bye.
Bye. Okay.